Hello and welcome to this discussion about several of the distributions, probability distributions that are for categorical variables. And these include the chi-square, the binomial, and the Poisson distributions. I'm going to quickly go through the concept of the binomial and the Poisson distribution, but those are not as much of a focus that I would like to have as the chi-square distribution. So let's think about the binomial distribution. And you have an entire chapter in your book on this. Unfortunately, in typical public health published literature, we don't use binomial very much, but it's good to have heard about it and to understand it. So here's my short abbreviated version of binomial distribution. The kind of question that binomial can answer is of n Bernoulli trials, and I'll come back and say what those are. What is the probability of X successes? And so a Bernoulli trial, you could actually think of this as each patient or subject in your trial or in your study. Could be cross-sectional, could be any kind of different study design. Doesn't have to be a trial, so that's a little bit misleading. But a Bernoulli trial simply means that for each person, they have either a positive or negative response to something. So it could be yes, no, it could be any variable that is dichotomous. So I'll just put a D here for dichotomous. So if the subject has the disease or does not have the disease, if the subject is male or female, if the subject is sick or not. So a Bernoulli trial, by definition, it just simply means that for each subject or unit that you're measuring, there is either a plus or a minus for that particular dichotomous variable. Now, by success, that's also kind of a tricky term, because success kind of implies something positive. In this case, it could be positive or negative. What is the probability of so many people in that particular sample having diabetes? I'll just say DM for diabetes mellitus. So I would not personally consider having diabetes to be a success in my life if I had diabetes. But what that means is that you have whatever it is that is that positive response, whatever it is that you've defined as that thing. And so it could be that success versus not success is smoking versus not smoking. And the interesting thing about this, because of the way the probabilities are set up to be complementary, the probability of success versus failure, both of those things are in the equation, and so they really are interchangeable. Success could be that you exercise every day versus you don't exercise every day, and you can choose either one of those categories as the plus version of your outcome. So here's the equation, and I only give that to you so that you can have seen that it has this probability of success, here's the P, and the probability of failure, or Q. Those two things by definition must add up to be 100%. So if your success is 20%, the probability of success is 20%, then the probability of failure must be 80%. And so those two things are complementary, and this is exactly why we can define success in either way. So success might be having diabetes, or success might be not having diabetes. And then the other group is automatically included in this particular equation over here. So the important thing to remember about binomial is that by definition you have a dichotomous variable, so you have two categories, and you want to know what is the probability that you will have a certain number of successes. So let's go ahead and draw something that looks like that. And you have an example in your book that has to do with responding to treatment. And so let's say that here on the left axis is the probability of exactly that, responding to that particular treatment. And if you have 4 subjects, so here we have the probability that none of them would respond to treatment, that only 1 would, only 2, that 3 would, or 4. Now in this particular example, the probability for success is 75%. So you'd expect there to be quite a group here at the 75% mark. And actually what this looks like is it's a pretty low probability for 0. It's kind of like a sort of the probability of having 1 person that responds to treatment out of the 4, the probability of 2, and then 3 is by a long stretch it is definitely the highest, and then 4 is another good possibility. So take a look at that example in your book, and these would be, whatever probabilities along the left hand side, 10, 20, 30, 40, and so on. And again, these probabilities, each of these levels, this really needs to add up to 100% because these are your only choices. And so that's kind of a rough picture of kind of how probabilities work. Part of the reason that I don't go into this too much is that you would be using probably a computer program, because you would have more than likely you would have a lot more than just 4 groups. You would have 20 or 50 subjects in your trial, and so then that becomes a lot more challenging to calculate by hand. The other thing is that the equation here for this particular piece actually expands out to something that's quite a bit more complicated than just that particular thing. It includes factorials, and so kind of by definition, we would, in order for us to be sure that we're calculating things correctly, we generally use computer software to do that. So I'm not asking you to calculate those probabilities. You probably, if you're a biostat or an epi major, you probably learned this already, and so you know how. But again, we're going to be doing things that are quite a bit larger of a sample size than what we do in kind of short exercises. So that isn't as useful as knowing how to program that in SAS or some other computer program. So that is the binomial probability distribution and kind of what that looks like. It starts looking like a normal curve. You can imagine the larger and larger that sample gets. All right, so Poisson, the French pronounce this without the N, of course, they Poisson. And I'm probably slaughtering that if you speak French natively. So this is a little bit different than the binomial distribution. This has to do with the probability of a certain number of events occurring during a specific time. So let's say that we have a time period for, and I'll just say for the ER, emergency room or emergency department, let's say from 11 p.m. to 5 a.m. Usually, on average, we get, say, 5 patients. We're a little ER, doc in the box kind of ER in a small rural town, and we see a few patients every night, but not very many. Sometimes it's 4, sometimes it's 6. And I would like to know what the probability is of a specific number of X events. And again, you can see the equation over here on the right hand. It has a factorial in it. And we need to know the number of events that we're testing for. Let's say we, on average, have this situation where we have 5 events, and we want to test what are the chances, what's the probability of having only, say, 3 visits that particular night, or what if we want to know what are the chances of having 10 for that particular time frame. One of the requirements is that the probability of each event needs to be independent, and so they can't come in clumps like earthquakes do and that kind of thing. So they need to be independent of each other. One person coming to the emergency department isn't because or dependent on another patient coming in to be treated. So they're independent, and it's pretty constant over this whatever time frame we choose. And so we probably wouldn't want to choose the same use the same equation for, say, 11 p.m. to 5 a.m., kind of the middle of the night kind of probability, as we would for 6 a.m. to 10 a.m., which tends to be a time when a lot of people wake up in the morning, they realize their kids are sick, and so then they have to take them to the emergency department. So we need to know the number of events that we're testing. So that's one of the requirements. And we need to know the average. What do we typically have? And so this is 5 for any equation. And then also this equation uses E, which is just a specific number in math, 2.71828, and it keeps going on and on and on. And so basically we're taking those numbers, whatever they are, and we're plugging them in to this equation. Again, we have a factorial in it. It's not as important for you to specifically know how to hand calculate that. If you ever needed to do it and you were an epi-biostat major, then you could probably look this up, or maybe you use it all the time and you would just have it on your brain to be able to access that. The main thing to remember, though, is that here we're defining a specific time, and our probability will be about the same throughout that. This often helps us in public health in terms of kind of resource allocation or staffing. And so you can imagine if we can say, okay, the probability of, we usually have 5, the probability of having 10 is like less than whatever. It's really small. So we're going to not staff for that. We're not going to spend the money on that, and we're going to have a backup call system where we do call people in and maybe pay them overtime for that rare event where we have so many patients arrive during that particular shift. So it may have to do with how quickly materials are used, but it's not the same as the binomial distribution. It answers a different type of question. So and I'm not going to draw a new graph, but it's a different equation. Clearly this is mathematically different than the one we had for binomial, but it looks quite similar to the binomial distribution in terms of each particular value has a given probability of occurring, and this just kind of goes on indefinitely because it's not bounded. So those are a couple of differences between Poisson and binomial. Now, having said all of that, it's really helpful to understand binomial and Poisson distribution. However, I see it very rarely in the published literature that I'm reading, and I don't use it very often in anything that I'm doing. So it's helpful to understand different distributions, but I think it's much more helpful to focus in on the chi-square types of tests that we need to know about. So I will not be including binomial or Poisson on exam questions. It is theoretically possible for those to be included on your, say, CPH exam, because they are included on the exam content outline. And so that's why I wanted you to know about them. But in terms of being able to actually apply things to your practice of public health, I would say focus more on the chi-square. Okay, so here we have 2 chi-square tests. I can see if I can fit them all on the screen. So both of these have the same distribution. And what I'd like to do is point out an example so that you can understand the difference between them, and then I'll draw kind of what a typical chi-square distribution looks like I did for the other 2. But we'll wait to do the math on these 2 examples until the next video. So this is just about understanding the distribution. So for the chi-square goodness of fit, this answers the question for a categorical variable: how well does the sample that I chose fit a specific proportion for each category? And you could replace that with percentage, or how is it balanced between those two? Are they equal? That would imply that the proportion is 50-50. So that's the kind of thing that you're looking for in a chi-square goodness of fit. And so specifically, I help people remember this by saying you have a good fit. And here we have how well does the sample fit. In English, if I crossed this off and I said good, my English teacher, Dr. Gray, would probably roll over in his grave. How good does the sample fit a specific proportion for each category? So here you have the chi-square goodness of fit. And the thing that I want you to notice about this is that we have for a categorical variable, for one categorical variable. So this is just one categorical variable all by itself. And so let's say that we have this example, and we'll start filling it in just a little bit, just enough so that you can see kind of what we're getting at. First of all, we need to know the observed number for each category in our sample. So we would take our sample and we would ask each person, are you a smoker, are you a non-smoker, and we would fill in whatever the numbers are that go here. And so that's our observed number. I'm going to get rid of that just so that those aren't filled in when we get to it later. Then I need to know the expected number for each category. And let's say that I expect there to be 25% of the population be smokers and the other 75% be non-smokers. If I have a sample size of 80, then I can calculate how many I would expect, how many expected I would have for here. So you can do that kind of in your head, probably 25% of 80 and so on. So that's the kind of question that we're asking, and I need to know the observed for each category in my sample, and I need to know the expected number for each of those categories. And then later on you'll see exactly how the math works for that. The chi-square test of independence is also sometimes called the chi-square test of association. And it's interesting because this is the only time in a common statistical test that the actual name of the test really shows what our null and alternate hypotheses are. And so let me just give you the generic version of this. For two categorical variables, is one dependent on or associated with the other, or are they independent, not associated? And so you can see how if I say test of independence, that means they're not associated. If I say that they're associated, that means that one is possibly dependent on the other one. And so they're just two different ways of thinking about the particular hypothesis that we're testing. Remember, the null hypothesis usually means there's no association, they're not related to each other, there's nothing interesting going on around here, one is not dependent on the other. And then the research hypothesis, or the alternate hypothesis, is usually the one that we're interested in. We want to see, does this particular thing, this variable I can measure, does it impact whether a person has disease? Does it impact whether a person is in a particular category? So for two categorical variables, and we want to know if they're related to each other, this is called the chi-square test of independence, and it can also be called the chi-square test of association. So are the two variables independent from each other? Are the two variables associated or related to each other? And not surprisingly, since we have a chi-square here, that we use the same math behind the scenes, except there's a little bit of a difference here. For the chi-square test of independence, we want the observed number for each combination in your sample. So in this example that I have over here on the right hand side, I have smoker and male female. So smoker non-smoker, male and female, and I need to know how many this observed value for each combination. I need to know how many male smokers I have. I need to know how many female smokers I have. I need to know how many male non-smokers I have and how many female non-smokers I have. And again, the thing that I'm doing is I'm also looking at the expected values for each combination. And so I would want to have both the observed and the expected for each of those pairs. Now this, the chi-square goodness of fit and the chi-square test of independence are not limited to dichotomous variables. We'll talk about that in the next video. They're just simply the easiest one to learn about because we don't have to do quite so much math. But the chi-square test can be expanded to be a 2 by 3 table, a 2 by 10 table, a 3 by 5 table, all kinds of combinations. And so it's important to remember that it can be flexible. So the one thing that I did want to show you is for both of these chi-square, and I'm going to see if I can kind of squeeze it in here in the middle. There's a distribution that is actually a family of distributions. Just like we had sort of a family of the t-distributions, it depended on the degrees of freedom that we had. This is exactly the same, and I will talk about degrees of freedom in the next video. But in general, that chi-square distribution for a reasonable sample size looks something like this. And so here we have kind of like that probability going down and down and down, and at some point it gets less than 0.05, and we would say, what are the chances that we would have a certain finding in any particular cell such that it ends up being maybe out here in the tail. So that's exactly what we're going to look at when we move on to our next video, where we're calculating the expected values and also calculating the chi-square test statistic. So thank you for joining me for this video.